Position sensors report the physical position of an object with respect to a reference point. The information can be an angle, as in how many degrees a radar dish has turned, or linear, as in how many inches a robot arm has extended. We will take a look at potentiometers, or POTS. A potentiometer can be used to convert rotary or linear displacement to a voltage. Actually, the pot itself gives resistance, but as we will see, this resistance value can easily be converted to a voltage. POTS used for position sensors are the same in principle as a standard volume control on a radio or TV, but there is a difference. A pot used for a volume control may have audio taper, which means the resistance changes in a non-linear fashion to match the human perception of getting louder. A pot used to measure angular position has linear taper, which means that the resistance changes linearly with shaft rotation. Figure A illustrates how the pot works. A resistive material, such as conductive plastic, is formed in the shape of a circle, terminating at contacts A and C. This material has a very uniform resistivity, so that the ohms per inch value along its length is a constant. Connected to the shaft is the slider, or wiper, which slides along the resistor and taps off a value, contact B in Figure A. Figure B shows the circuit symbol. The pot just described is the single turn type, which actually has only about 350 degrees of useful range. A single turn pot may have stops at each end of its travel. Obviously, such a pot could only be used when the rotation never exceeds 350 degrees. A single turn pot without stops has a small dead zone when the wiper crosses the end of the resistor. Multi-turn pots are available with the wiper that moves in a helix motion, allowing for up to 25 or more revolutions of the shaft from stop to stop. Figure C illustrates a linear motion potentiometer. In this case, the wiper can move back and forth in a straight line. Linear motion pots are useful for sensing the position of objects that move in a linear fashion. Figure A shows a pot that detects the angular position of a robot arm. In this case, the pot body is held stationary and the pot shaft is connected directly to the motor shaft. 10 volts is maintained across the outside terminals of the pot. Look at Figure B and imagine how the voltage is changing evenly from 0 to 10 volts along the resistive element. The wiper merely taps off the voltage drop between the contact point and ground. For example, if the wiper is at the bottom, the output voltage is 0 volts corresponding to 0 degrees. When the wiper is at the top, the output is 10 volts corresponding to 350 degrees. In the exact middle, a 5 volt output indicates 175 degrees. That's 350 degrees divided by 2. The transfer function can be calculated as follows. Remember, transfer function is output over input. In this case, 10 volts DC is the output, 350 degrees is the input, which gives you 1 over 35 volts DC per degree. The potentiometer circuit being discussed here is actually a voltage divider, and to work properly, the same current must flow through the entire pot resistance. A loading error occurs when the pot wiper is connected to a circuit with an input resistance that is not considerably higher than the pot's resistance. When this happens, current flows out through the wiper arm, robbing current from the lower portion of the resistor and causing the reading to be low. To solve this problem, a high impedance buffer circuit, such as the voltage follower discussed in Chapter 3, can be inserted between the pot and the circuit it must drive. Loading error is the difference between the unloaded and loaded output. And loading error is VNL minus VL, where VNL is the output voltage with no load, and VL is the output voltage with load applied. In many applications, the total rotary movement to be measured is less than a full revolution. Consider an arm that moves through an angle of only 90 degrees. Using as much of the pot's range as possible in order to get a low average error rate is advantageous. So we might use a 3:1 gear ratio that causes the pot to turn through 270 degrees. The small pot gear must make 3 revolutions for every revolution of the motor gear. The controller will be programmed to understand that 3 degrees of pot corresponds to only 1 degree of actual arm. As in all physical systems, we must be aware of certain errors that creep in. In this case, carbon pots cannot be made perfectly linear. So we define linearity error as the difference between what the angle really is and what the pot reports it to be. The graph shows the ideal versus actual resistance for a pot position sensor. The error is the difference in resistance between these two lines. Notice that the error is not the same everywhere, but the maximum error is designated as delta R. Linearity error is defined in percentage, as shown below, and ranges between 1 and 0.1%, but a higher precision costs more, of course. Linearity error equals delta R times 100 over the total resistance. When the potentiometer is used as a position sensor, the output voltage is directly proportional to the shaft angular position, so linearity error can also be expressed in terms of angle, where the linearity error is equal to the change in angle divided by the total angle times 100. Now let's look at an example. A single turn pot has a linearity error of 0.1% and is connected to a 5V DC source. Calculate the maximum angle error that could be expected from this system. So our solution is to calculate the maximum possible angle error. We rearrange the linearity equation and we solve. So delta theta is equal to linearity times the total angle divided by 100, which gives us 0.35 degrees. If this pot were in a control system, the controller would only know the position to within 0.35 degrees, or about 1/3 of a degree. Linearity error determines the accuracy of a sensor. A related but different measurement concept is resolution. Resolution refers to the smallest increment of data that can be detected and/or reported. In digital systems, the resolution usually refers to the value of the least significant bit, because that is the smallest change that can be reported. For an analog device, such as a potentiometer, resolution refers to the smallest change that can be measured. It is usually expressed in percentage. The percentage resolution is equal to the smallest change in resistance divided by the total resistance times 100. Or delta R over R tot times 100. Let's examine resolution in conjunction with the wire-wound potentiometer. A wire-wound pot uses a coil of resistance wire for the resistance element. The wiper bumps along the top of the coil. Clearly, the resolution in this case is the resistance of one loop of coil. This concept is illustrated in the next example. Example 6.4. The resistive element of a wire-wound pot is made from 10 inches of 100 ohm per inch resistance wire and is wound as a coil of 200 loops. The range of the pot is 350 degrees. What is the resolution of this pot? Solution. The total resistance, R tot, is equal to 10 inches times 100 ohms per inch, or 1000 ohms, or 1 kilo ohm. The pot coil has 200 turns of wire, therefore the smallest increment of resistance corresponds to one loop of the coil. The resistance of one loop of wire is total resistance divided by the number of loops, or 1 kilo ohm divided by 200 loops, which is 5 ohms per loop. Thus the resolution is delta R over R tot times 100, or 5 divided by 1000 times 100, or 0.5%. If you look in the book, you will see the slight error. They recorded 1 kilo ohm as 1 ohm. But this slide is correct. If this pot were to be used as a position sensor, it would be useful to know what the resolution is in degrees. The smallest measurable change corresponds to one loop of the resistance coil, and this pot divides 350 degrees into 200 parts. Therefore, the resolution in degrees would be 350 degrees divided by 200 loops, or 1.75 degrees. An alternative method is to take 0.5% of 350 degrees, which is also 1.75 degrees. Why not check this for yourself? The output of a position sensor should be a continuous DC voltage, but the slider action of pots can sometimes cause voltage transients. This is particularly true for wire-wound pots because the slider may momentarily break contact as it bumps along from wire to wire. If this is a problem, it can usually be resolved with a low-pass filter, which is simply a capacitor to ground. The capacitor stays charged up to the average pot voltage and resists momentary voltage changes. Another example, the robot arm illustrated in figure 6.7 is rotated 120 degrees stop to stop and uses a pot as the position sensor. The controller is an 8-bit digital system and needs to know the actual position of the arm to within 0.5 degrees. Determine if the setup as shown will do the job. To have 0.5 degree resolution means that the entire 120 degrees must be divided into 240 increments, each increment being 0.5 degrees. An 8-bit number has 255 levels, from 0000, 0000 to 11111111. So it has more than enough to do the job. That's good. The pot is supplied by 5 volts, therefore the output of the pot would be 5 volts for the maximum pot angle of 350 degrees, if it could rotate that far. Notice that the reference voltage of the ADC, the analog to digital converter, is also set to 5 volts. Thus, if the pot voltage, V pot, is 5 volts, the digital output would be 255, or 11111111 in binary. Table 6.1 summarizes this. See the last 3 columns. A single turn pot has a range of 350 degrees, but the robot arm only rotates 120 degrees, hence the 2-to-1 gear ratio between the pot and the arm. With this arrangement, the pot rotates 240 degrees when the arm rotates 120 degrees. By doubling the operating range of the pot, the linearity and the resolution errors from the pot are reduced by half. Consider the case when the robot arm is at 10 degrees. It's the second line in the table. Because the 2-to-1 gear ratio, the pot would be at 20 degrees. To calculate the pot voltage at 20 degrees, we use the transfer function of the pot, 5 volts divided by 350 degrees. Voltage V pot is equal to 5 volts divided by 350 degrees times 20 degrees, or 0.29 volts. This 0.29 volts is converted into binary with the ADC. To calculate the binary output, first form the ADC transfer function. Output over input is equal to 255 states divided by 5 volts. Now calculate the ADC binary output using the 0.29 volt, the pot voltage, as the input. So 255 states divided by 5 volts times 0.29 is equal to 14.8, or about 15 states, which is 00001111 in binary. We now turn our attention to the system resolution, which is the smallest measurable change. In a digital system, this usually corresponds to the value assigned to the least significant bit. You can't change half a bit. We can find the resolution by calculating the pot angle corresponding to a single binary state. This is done by multiplying the transfer functions of each of the system elements together to get an overall system transfer function. You may notice that we actually use the inverse of the transfer function in order to get the desired units. So 1 degree of arm over 2 degrees of pot times 350 degrees of pot over 5 volts times 5 volts over 255 states all comes out in the wash at 0.686 degrees of arm per state. This result tells us that the least significant bit of the ADC is 0.86 degrees, which is too big. We need the LSB to be 0.5 degrees. As it stands, this design does not meet the specification, but can it be fixed? Yes, looking back you can see that at 350 degrees the pot sends 5 volts to the ADC. But this will never happen because the pot is constrained at 240 degrees. To get maximum resolution from the ADC, the pot should send 5 volts to the ADC when the pot is 240 degrees. This will require raising the pot supply voltage to 7.3 volts by voltage ratio. The revised voltages are shown. Now the resolution is recalculated to be 1 degree of arm over 2 degree pot times 350 degrees of the pot times, or divided by 7.5 volts times the 5 volts divided by the 255 states, which all comes out in the wash as 0.47 degrees of arm movement per state. This result is within the 0.5 degree specification for resolution.